Yes, am I audible? I think screen visibility, audio, and recording is on. So we'll continue this unit 4 and we'll try to complete today. Okay. Now coming to the remaining part of this unit 4, that is cost reduction factors of PV systems or any solar system. So that we have to discuss and we have to take some numericals on this solar PV systems. Okay, that completes unit 4. So first we'll start with the cost reduction factors. So first here, as I explained in the earlier classes, just a minute, I'll make it full screen. Yeah. So coming to the cost reduction factors. So first thing is the high priced systems of solar energy, like concentrating systems or thermal systems, or you can say PV systems. So to reduce that cost of the high priced systems, first thing what we have to do is we have to come up with the new materials or new mechanisms or new production techniques through which we can reduce this production cost and the material cost of the PV systems. So focusing on this, we need to go for innovation or researches required nowadays, and also we need to develop very new improved techniques which are reducing the production cost, as well as on the material also we need to concentrate on which the band gap or energy gap, as I said earlier. So such materials we need to find out with a very low band gaps and also possibility of getting the material at very low cost. So even though silicon was very comparatively less cost available, but keeping in mind of production technologies and techniques what we are using for single crystal or the multi crystal silicon cells. So to reduce that production cost also we need to come up with the new innovative ideas. So here we need to focus more on the production technology as well as material cost. Both are going to affect. And keeping in energy cost, so as the solar energy is freely available, like wind energy or ocean energy, similarly, for the energy there is no cost. So we are going to assume the energy cost is zero. Okay, so we have to focus more on the reducing the cost of concentrators, wastage of the materials in production or while purifying the material, that wastage we need to overcome, and the production techniques we have to improve, and a lot of innovation is required so that we can improve the efficiency of the solar cells. Now, apart from this, if you focus on the 2020 data, the solar power present total installed capacity, you see, so that capacity is around 35 gigawatt as of 2020, and the price per unit, if you see, it is around 2.62 rupees per unit. Okay, from the solar panels, or you can say for 1 kilowatt hour per unit, 1 kilowatt hour, the cost is around 2.62. And the lowest price of the panel per watt in 2020, if you see, the lowest price of the panels is around 35 rupees. So that much cost effective is achievable up to 2020. So similarly, you can get the data of 2021 year. In that, what is the per unit price from the solar energy that you have to check, and also per panel, what is the cost. So in this thing, we have to later we are going to focus on the economics of the solar energy. So there, these all things will help us, because nowadays, if you see any system, if you want to apply or if you want to use it, the first thing comes in the mind is the what is the cost incurred, initial cost, and the profit over the years what I am going to get, and whether this solar system is going to compete with the fossil fuels or the conventional fuels what we were using earlier. Is it competitive or is it going to profit us over the years? If that is advantageous compared to other systems, then we can think of these solar systems. So till today, little bit achievement is possible by a lot of innovations, and also many states have been planting these solar PV systems as well as the thermal systems or the power plant systems. So many countries also having solar power plants, so by which they are turning that fossil fuel burning into this using of free energy. Okay. So next you can see the solar plant owner would be receiving nearly double the price of electricity sent into the grid. Okay, that compared to the consumed from the grid. So if you see the grid connected systems, as we discussed in the earlier topic, like this grid connected system, if you see here, whatever the amount of power generated from the PV cells on the buildings or on the given wastelands, so that energy, if he supplies to the grid, the government should provide him double the price of whatever he has sent. So per unit, whatever the price is there for the from the grid, whatever you are using now, 5 rupees or 6 rupees per unit. So double of that price can be given by the grid systems of the government, because he is sustainable energy he is providing, and also he is dependent on the his own energy system which is on the building. So keeping this on mind, and also he is supplying the power whenever the grid is not running, or whatever the stored energy is there, he can also supply to the other buildings. So in that case, later we can come up with the agreements so that the price can be improved. So keeping that, he can give the double price. Also, whatever the energy he is using from the grid, if he is connected with the solar system, then that grid price, or the price of the our agreements can be made in the discount is given for the solar energy. Okay, so that can be done on depending upon the power frequency of the energy, okay, or the voltage current. Depending upon that, he can get some more profit from the solar PV system. So that can be improved. Also, as already you know, we are using the wastelands. Okay, still we have more wasteland where the proper forest is not available, or the land which is for water storage also. In such cases, wherever the wasteland, if you feel, so that wastelands can be found out, and some survey, after surveying, we can go for the wasteland usage for this solar PV system, for the solar thermal systems. And also large buildings, big buildings are built now. So on the walls or the top floor or the open space at the top, so there we can go for this solar system. So already these are things are done, but coming days, one should think of each building should have these solar systems, or any wasteland is available. In that, you can just keep a solar system and you can generate some energy. Okay, or say for example in farmlands, so whenever there is a crop cultivation is not happening, or the crop is taken out, after that, say for example 2 3 months, if the land is not used, in such cases we can go for assuming that is a wasteland for a given time, and up to that we can generate some power and can give to the government. So coming to the problems, so before going to the problems, as we discussed in the class also, we'll recall some equations which are useful for the numerical examples. Then we'll solve the numericals. So here you can see, to find the maximum power, what you have to do is you have to multiply the maximum voltage and the maximum current that is coming from the cell. So from that, one can get the power available in the given cell. And to find out the fill factor, or open circuit voltage and the short circuit current, we can use this equation. This is the fill factor equation. That is the product of maximum voltage and maximum current from the cell of the solar cell to the product of open circuit voltage to the short circuit current. Or in place of fill factor, you can find out either the maximum power and maximum voltage product, how much it is available, or product of voltage and current. Using this, one can find out the maximum power point or maximum power from the circuit. You can see here, maximum power point, if you see, we can multiply maximum voltage and maximum power. If one can find out the just the power or the maximum power available from the cell, one can go for using this product, that is short circuit current into open circuit voltage. So by that, one can find out the power available or the maximum power available from the cell. If it is maximum power point or the maximum power what is available, you can multiply with maximum voltage and the maximum current. Okay. Next is with the efficiency. Now with the efficiency, what equation we can write is output by input power. If you take the ratio, so already we know the output power from any given cell. That is the maximum current into maximum voltage. So that you can multiply. Even though if you don't know any of these maximum values, then I can go for using this fill factor equation. Means I'm going to replace this VMP and IMP with this product of fill factor and voltage and current with respect to open and short circuits. So that if I multiply here, I can get also the maximum power available from the cell. Okay. So using these details, now we'll see the numericals. How in the numericals these equations will help us. So now we'll take the first numerical. Considering the solar radiation of 200. So here in the problem you can see joules per meter is given, meter square is given. To convert this into watts, joules per second, if you convert, means you are going to multiply 200 to 60. So that will turn into very huge value. So we'll keep this 200 joules per meter square as 200 watt per meter square only. Okay. So that first correction you can make out 200 watt per meter square you can consider, and per unit time. So for a given time, okay, during daylight, for a given unit time, the solar radiation falling on the cell is 200 watt per meter square. That I am going to take. Find the area of the PV cells needed to generate enough electricity to run. Okay, now here we need to find out what is the area of the PV cells required to run different electrical appliances. Okay, so that will generate some enough power to run these different systems. So first one is a desktop computer using 400 watt. So to run this desktop, what is the area of the PV cell is required? That we need to find out. Next case is an electric geyser is using 1 kilowatt power. So for that, how many cells are required, or what is the area of the cell is required? That you have to find out. Third device is a toaster using 500 watt. So these are the three devices separately they have given. So for individual device, what is the area of the PV cell required? Also in the end they have given assume the efficiency of PV to be 25%. So this will help us in finding what is the actual energy per meter square of the cell is generated because of the efficiency. If efficiency is not given, I can take 200 watt per meter square directly, so that assuming 100% the solar cells are converting the solar radiation into electrical energy. Okay, so that may be not be possible. So in such cases, they will give the efficiency. Now coming to the first case. As for the given data, I will start with the first case. So for the desktop computer, 400 watt power is required. So there is one power for the appliance required is 400 watt. Now for this, I want to find out what is the area required. So in such cases, if I want to find out area, I can take watt and what is the power developed by each cell per unit area. If you know that, I can take this 400 divided by 50 divided by 50 watt per meter square. But where this 50 comes from? Okay, that is the power output from each cell. If you want to find out, what I can do is I can multiply this efficiency with this power. Why? Because the power is 200 from the solar energy, not from the cell. Now, once this solar energy is converted from 200 through the PV cell, what is the efficiency? It is only 25%. So once you multiply this 0.25 and 200, I will get per cell or per meter square. Okay, per meter square. What is the power generated? It is only 50 watt. Is that clear? So this 50 watt I will consider, assuming per meter square. I will take 400 divided by 50. Then the answer I can write it as, after cancelling wattage, both the wattages and left with meter square. Here 400 watt divided by 50 watt per meter square of area. If I take, the answer will be 8 per 8 meter square. The meaning is we need to use 8 meter square PV cells for the running of computer or a desktop. Because they are not asking number of PV cells, because number of PV cells means we should know the area of the PV cell also. So that is not asked here. They are asking only area. So area, if it is required for cells, I need 8 meter square area, 4 by 4 or any type of size. It may be rectangle type or the square. Next case is electric geyser. So in this, what is given power? The power required is 1 kilowatt. So 1 kilo means 1000 watts. So for 1000 watts, you can take 1000 divided by 50 watt per meter square. If you take, I will get area around 20 meter square. So to run the geyser, electric geyser, we need high power. Okay. So for that, as per the given energy and conversion efficiency, the area required to make the PV system is 20 meter square. Similarly, if you see the toaster, so toaster power required is how much? 500 watts. For this 500 watts, again what I will do is I will take the total power required, okay, divided by power per meter square what is available. If I take the ratio, I will get 10 meter square. Now to generate the power for 500 watt toaster, okay, I have to implement the PV cells for 10 meter square. Now for the total load, so even though in the question they have not asked for what total load, you have to get the maximum area. But assuming these all instruments are in a home or in a building or in a given single place, and we want to run these all three systems. Okay. So what I will do is I will take the total load now, 400 watt, 1000 watt, and 500 watt for the desktop, one geyser, and toaster. I'll add all the loads, and total area for this to run is sum of the all the areas. So that is 8 meter square for the desktop. For geyser it is 20 meter square, and for the toaster it is 10 meter square. Once you add these all areas, I will understand that to run this 1900 watt, I need 38 meter square. So like this, for a given applications, knowing the efficiency of the PV cells and what is the solar radiation possible for per day or per given time, so one can find out for the number of bulbs, number of appliances in the home, or number of different devices to run in the home, what is the total load is there, and what is the total number of cells or number of areas required to implement this solar system. If that area is available for the building, you can go for that. Or else you might have heard outside that only for the lighting we have taken the solar system, and remaining to run the appliances we are using the grid connection power. So like that, as per the required area and as per our convenience, because even cost is also very important, because all the people cannot buy solar system only and they can generate the power on spot. Okay, keeping that financial problems and also the area problems, one can think of only going for the lightings or only going for the selected equipments. One can use that waste land and he can generate some power and he can run at least one or the two devices in the home. Okay, so for that I have taken this example. So just you can take 1.5 minute and you can just check the procedure what we have followed. Okay. Next problem you can see a heterojunction solar cell. So heterojunction in the sense P and N junction, not a common junction. Both are different junctions are combined there. So that's why it is called as a heterojunction solar cell of active area 6 centimeter square. Gave the following results. So what is the meaning of this is a PN junction solar cell of area 6 centimeter square gave the following results. When solar radiation is falling or any light is falling on that solar cell, what is the results they have? It has given for 6 centimeter square. It has given Open circuit voltage 400 millivolt is given. Short circuit current, so I can write it shortly at ISC, 200 milliampere. Okay, this is at the maximum power here. What it means is open circuit voltage and short circuit current is without connecting to the load. Okay? Without connecting to the load, whatever the voltage is generated, the maximum voltage is generated here. Open circuit voltage means circuit is open. At that moment, to just check the voltage between positive and negative P and N junctions, that voltage is how much? That is given. One more is short circuit current. If you just short the circuit without any load, then what is the maximum short circuit current? Both values are given. Next, according to the fill factor, it is going to give the maximum voltage and the maximum current for this maximum power part. So these all values should be given here. You see the problem. Yes. For this, open circuit voltage is given 400 millivolts. Short circuit current is given 200 milliampere. So all values are giving in milli. Okay. So let we will see what to be converted. Under an insolation equal to zero point 0.8 sun. So insolation, as I told, the solar radiations falling on a given area, we can call it as insolation. So that insolation is equal to 0.8 times sun, means it is not complete one sun. Maybe due to more diffuse radiation and the radiations can take 1000 watt per meter square. So for 0.8 sun, you can convert that into a different watt per meter square. That will come around 800 watt per meter square. Later, for convenience, for same units, I can convert that into milliwatt per centimeter square. So 800 watt per meter square, you need to convert into milliwatt per centimeter square. So please check that value, how much will get. The question is, what is the energy conversion efficiency? Now you need to find out here in this problem, you need to find out efficiency. Efficiency is not given. Find out the efficiency or energy conversion efficiency of the device. Device means here only solar cell. Assume fill factor 80%. Okay, now in this problem, fill factor is given. Open circuit voltage, short circuit current, both are given. Not the maximum or the maximum current is given. Area of the solar cells, complete area of the solar cells is given. Then insolation or the power supply is 0.8 sun, or you can say 80 milliwatt per centimeter square for conversion. Okay, and after all these things, knowing the fill factor 80%, we need to find out efficiency of the solar cell for 6 centimeter square. Okay, first one will take the finding the maximum power output from this device. Okay, that is the maximum power point. To find that, we know fill factor is the ratio of products. Fill factor is given by VM IM or VMP IMP divided by VOC divided by ISC as per our theory. Now taking these known values one side and unknown values one side, okay, one can find out what is the maximum power generated in the cell. That is, open circuit voltage 400 milliwatt is given, millivolt is given. Short circuit current is also given, that is 200 milliampere. Okay, so you can keep in milliampere or amperes. Then fill factor efficiency is 80%, so they have taken 0.8. Now using all these values, you can find out what is the wattage in milliwatts. So please check the values for the correctness. 400 millivolts, 200 milliampere is given. They have taken 0.2 amperes only directly. Okay, the ampere value is directly taken in point 2, and they are getting 64 milliwatts as per the point 2 amperes. The value is 64 milliwatts. Next, using this maximum power point, okay, so later, because this is required for our efficiency only. Efficiency is what? Maximum power output from the cell to the total solar insolation. Now for the total solar insolation, what you have to do is, or the energy supplied, power output is known to us, power input is not known. It is known indirectly, that is 0.8 sun. Okay, so 0.8 sun means I can tell 800 watt per meter square. So once you convert that into milliwatt per centimeter square, I can, that you convert it into milliwatts. So that will be 80 milliwatt per centimeter square. And for the given area of 6 centimeter square, this is for per centimeter square. If you multiply with the given area, 6 centimeter squares, the total input power or the incident radiation is 480 milliwatts. Output power and input power. In percentage, I'll get 13.33 percentage. I can see for this solar cell for 6 centimeter square and solar radiation of 0.8 sun, whatever, and short circuit current or VOC. In this problem, the given values are like this. In other problem, maybe whatever the efficiency is there or the maximum power is there, it may be given in the problem. Later, we need to find out fill factor and other unknown values. That's here. So for the given values, you can see the efficiency. It is only 13.23%, not much. But finally, what is happening? Even though if you install this with the initial cost and other thing, energy cost is zero. Okay, that's what efficiency is not important, but we are generating some energy. Okay, using, as I told, maybe in the next problem we are going to find some other values. Okay, any equation you know already, any equation or the formula properly if you know, one can substitute the known values and one can note down the unknown value. In similar fashion, we are going to solve one more problem. We'll see one more problem and we'll stop the class at that moment, and we'll next class we'll see the economic analysis of the solar systems. So I hope this will be understood by all the students. Now, next problem I have taken, calculate the fill factor. Now see the reverse of the problem. Here we need to calculate. Calculate the fill factor, maximum power, okay, maximum power and cell efficiency with the following. See here, now what they are asking is, fill factor we need to find out, maximum power we need to find out, and efficiency also we need to find out. All the factors we need to find out, and also we know the formulas for all the factors. So for that formula, what need to be substituted, whether it is given or what, we need to check. So parameters like open circuit voltage is current, voltage is given 0.24 volts. Short circuit current is also given, ISC is given 10 milliamperes. Okay, and maximum voltage is also given 0.14 volts, and maximum current is also given. See, maximum current and voltage, they will tell us the maximum power. Okay, so that only is given. VM or VMP is given 0.14 volts and IMP is given 6.5 milliamperes. Intensity of the solar radiations or the light which is falling on the solar cells per meter square is given, that is 24 watt per meter square, and area is 4 centimeter square. Now see, input power you can find out, output power you can find out. Okay, then we can find out efficiency also. Now coming to the fill factor, the formula is what? formula is maximum voltage into maximum current divided by the product of open circuit voltage and short circuit current. Sorry, open circuit voltage into short circuit current. If you take all the values and if you multiply and take the ratios in proper units, see, volts they have kept as it is 0.14, 0.24, and amperes, milliamperes you can see here, they have kept in same ampere values. 6.5 milliamperes, they have kept in 0.0065. Here also they have kept in 0.001 equal to point. How much you are getting now? Fill factor. See, not 80% here. In the earlier problem, it was 80%. Is that clear? But here, if you see, how much is the fill factor? Only 37.9. The fill factor meaning is now for the given solar cell up to around 38% or 38 part of the solar cell is converting solar energy into electrical energy. Is that clear? So that number indicates how many parts in the solar cell. Are the 100% converting? No. In the earlier problem, 80 part of the solar cell. If you see the screen itself, in the screen, if you assume this is a solar cell, out of this earlier problem, 80% of this screen or the face of the solar cell was converting into electrical form. But in this problem, if you see, as per the voltage and current values, it is only converting around 38 parts. So if you divide this screen itself, the mobile or the laptop screen, what you are seeing, out of this screen, if you assume this screen itself has a PV system or a PV cell, out of this only 38%, 38 parts of the cells are converting it into electrical form. That is the meaning of fill factor. So to improve this fill factor only, we are going for doping. So as you go on doping maximum impurities, then the fill factor can be improved. That's it. Now, using this fill factor, what can be done now? Just we'll see. Now next we can find out maximum power, because here we know the maximum power. In the earlier problem also we have found out maximum power, that is 64 milliwatt. That is nothing but Vm into Im. Similarly here Vm into Im can be found out either by taking fill factor into these values. But in this problem already we have given Vm and Im. There are two methods. Either you can find out fill factor into VOC into ISC to find out Im into Vm, or else you can multiply that ISC and Vm. All are independent. So now maximum voltage 0.14 volts and the maximum current in amperes if you write, so that you can write 0.0065. The value will be 0.91 milliwatts. So just check the values. Okay, it is coming 9.1 into 10 raised to minus 4, or in milliwatts if you want to write, you can write it as 0.91 milliwatts. Now the efficiency. The efficiency is nothing but same ratio, Vm Im divided by, you can take total input power. Total input power is nothing but the solar intensity, what is falling on the given cells for the given area. Now see the intensity of the solar radiation falling on the cell is given in watt per meter square. But the area of the cell, if you see, it is in 4 centimeter square. So both you need to convert and keep it in 1 units. So better what you can do is we can keep it in meter square only. Okay. So in meter square, if you want to write the bottom side, 24 watt per meter square, I'll keep as it is. 4 centimeter square, I'll convert it into meter square. So that can be written as 0.0004. If it is centimeter square to meter square. So please check that conversions. Now, if you write it in percentage, the efficiency is only 9.48%. From the total input energy of 20 watt, so 24 watt per meter square for 4 meter square area as a input power. Now, what is the output power from the cell is? Output power from the cell is 0.91 milliwatts. So according to that, percentage of conversion, if you see, it is 9.48%. Okay, I hope everyone has understood the formulas or the for efficiency, how to find out, or any unknown value may be given or asked. So according to that, you can take all the given data and you can check with different formulas, interrelate them, and you can find out the unknown values. You can just note down this problem. I'll give 1 minute and we'll stop the class. Later in the next classes, we'll start with solar economics. You can note down this problem.